Right, yes, let's get started. How's everybody doing? Good.
All right.
Alright, so let's continue where we left off last time. Last time we were talking about normal distributions. So we said a normal distribution is just a fancy word for bell curve, meaning exactly the same thing. We said that there were some variables in real life that were distributed in the shape of a bell curve. When we first started talking about this, some examples of such variables were weights, heights, IQ scores, and so forth. Vice versa, there are a lot of variables in real life that are not distributed as bell curves. For example, income distributions in the US are not in the shape of a bell curve. If you're taking a really easy test, the distribution for that easy test will not be a bell curve, and so forth. So let's look at one of those examples of variables that were in a bell curve, like weights. So let's say we're talking about weights of men. And you go out in the population and you gather a whole bunch of weights and you punch those numbers in your calculator. The calculator will give you the mean and the standard deviation. So let's say this is given. And again, you're told that weights of men are normally distributed. Or if you're not told that directly, then you can always plot the histogram of the weights that you do gather. And the histogram you'll see will be in the shape of the bell curve. So either you're told that the variable, weights in this case, is normally distributed, or you observe yourself through plotting histogram that it is in the shape of a bell curve. So we said that given that a variable is in a bell curve, now you can find the percentage of the population, or the probability that that variable, weight in this case, takes on values within any range. So for example, knowing that this weight variable is a bell curve, the mean is where the most number of people have that value. In this case, the mean is at 180. And so last time we started talking about, let's say we were interested in the percentage of the population that has a weight that's less than 215. So the probability of having this variable be less than this value of 215, we said this probability can be reduced down to an area under the bell curve. So having this variable less than this number is the same thing as the total area to the left of that number under the bell curve. So once we realize that probability can be equivalent to area, now there's a way for us to find that area using the z-score chart, the z-score chart in the book. So we said that to find this answer, we first have to convert this number to a z-score. So we want to find the z-score of 215. And remember we said the z-score of the data point was the number of standard deviations that data point is away from the mean. So we first find the number of pounds this data point is away from the mean by just subtracting them. So this is the number of pounds from the mean, 35 pounds. But there's 20 pounds for each one standard deviation, so to find the number of standard deviations away from the mean, we divide by the number of units for each one standard deviation. this is pounds per standard deviation. So the total number of standard deviations is 1.75. And this is the z-score, because the z-score by definition is the number of standard deviations that data point is away from the mean. So the z-score is 1.75. So recall that we said that a z-score is a signed number of standard deviations from the mean. So 215 in this case has a z-score positive 1.75 because it's to the right of the mean. We could also have a z-score that's negative 1.75 standard deviations, so on the other side, less than the mean. So a number of pounds that's 35 pounds less than 180, or 165, 145. So 145 would have a z-score that's negative 1.75 standard deviations from the mean. Okay, so once we get the z-score or number of standard deviations from the mean for this data point of 215, now we're ready to use the z-score table. And that table gives us a relationship between z-score and area to the left of that z-score under the bell curve. So remember that every data point here, like 215, that's going to have its own z-score. And then there's going to be an area that's to the left of that particular z-score, or an area to the right of that particular z-score. But the chart by convention gives us an area to the left under the bell curve. So the chart will give us an area to the left. So last time when we looked at 1.75, we got an area of 0.9599. Yes. So once we get this left area, that corresponds to the left area we were looking for all along, because we were looking for the probability of this variable being less than the number, and that corresponds to a left area. If it had been a probability of the variable being greater than the number, that would have corresponded to a right area. Okay, so this answer that we got represents the final answer that we want. So the probability of this variable being less than this number will be 0.9599. In other words, 95.99% of all men weigh less than 250 pounds. Okay, so that's review from last time. Any questions? All right. So that's the probability of this variable being less than the number. That's the same as the area to the left of the number under the bell curve. So what if we had wanted the probability of being greater than the number? What would change? Okay, so
you would take, you do the number 1 and subtract that z-score that we got from computing that for 9.9599, and then whatever is left over would be your answer for the percentage that is over 215.
Okay, excellent. So since we want a probability of the variable being greater than the number, visually, relative to this number, we want a right area under the bell curve now, and not a left area. So we want to find this right area instead. So our first steps are going to be the same as before. We find the z-score using this formula, or the definition of the z-score, and then we use the table to locate that z-score, and the table again will give us a left area, not a right area. But since we want a right area, and we know the total area under the bell curve is 1, this right area will be 1 minus the left area. So a right area under the bell curve is 1 minus the left area. So this answer that we get from the table representing the left area, we just subtract from 1 to get the right area. So this answer will be 1 minus this number. Okay, so this would be the probability of having a man that weighs more than 215 pounds. So it only happens 4.21% of the time. Any questions? All right. So then, last time we talked about, let's say that you wanted the probability, or let's say you wanted to find the weight that corresponds to the top 1% of all weights, the heaviest 1% of weights. So if we draw a picture of this distribution of the weight variable, we call it a bell curve. So there's going to be some weight here that we're trying to find, where only 1% of all men weigh more than that weight. So that means the probability of weighing more than that weight is 1%, and probability has an equivalency to area. So the total area to the right of the specific weight that we're trying to find is 1%. So before, we were giving a specific value of the weight variable, like 215, and asked to find either the left area or the right area, because we were trying to find the probability of being less than or greater than. So in this case, we're already given a right area at the end here, and we're asked to find the specific weight. So basically, we're starting at the end, and we have to drive exactly in reverse. So let's review. So this right area that we're given is 0.01. And then from there, we go in reverse. So we have to use the z-score table to locate an area that represents this right area that is 1%. So instead of looking at a right area that's 1%, remember the table lists only a relationship between left area and z-score. So how do we convert this right area to left area?
One minus the right area.
Yeah, good. So this data point here that has a right area of 0.01, the total area of the bell curve is 1, so the left area will be 0.99. So using the chart, we're going to locate 0.99 as a left area. Remember the z-score table, all the numbers in the first column represent z-scores, and all the numbers in the middle represent left areas, those z-scores. So here we're going to start in the middle to look for a number representing a left area. And find the number that is the closest, and last time the number that we found was the closest was 0.9901.
2.33.
And that corresponded to a z-score of 2.32. Anybody have any questions on using the table or anything else? Okay. So the closest z-score to 0.99 is 0.9901, and that the closest left area to 0.99 is a left area of 0.9901, and that corresponds to a z-score of 2.33. So now that we have the z-score of 2.33, we go here to find the data point, because our z-score before was from this formula. Z-score is x minus the mean over the standard deviation. So the circle quantity is what we're trying to find, x, and everything else we end up knowing. So we know the z-score that we just found from the table of 2.33. The mean is given as 180, and standard deviation is given as. So all we have to do is solve for x, and use basic algebra. So again, this is 2.33 equals x minus 180 over 20. So we're just going to do the same thing on both sides of the equation step by step until at the end we have a statement that says x equals something, and that'll end up being a truthful statement. So we'll multiply both sides by 120. Get rid of the denominator on the right. What was that? Oh, thanks. Multiply both sides by 20. And then now we're left with x minus 180 equals what's on the left. So the only thing preventing x from being itself is being subtracted by 180. So we're going to undo that, add 180 to both sides. So we'll get x on the right. Equals that. So now the data point we want is x equals this expression.
And you get 226.6.
226.6. That's in pounds. So that means that a man that weighs 226.6 pounds represents the heaviest 1%. There's only 1% of all men that weigh more than you. Any questions? Okay, so this is one way that you can find your data point x, is basically from the z-score formula, and basically just substituting what you know and solving for what you don't know, solving for x in this case. Another way that you can think about it is if you understand what it means to be a z-score. So the z-score of a data point, again, is the number of standard deviations that data point is away from the mean. So we're saying that this data point that we're interested in has a number of standard deviations from the mean that is 2.33. That means if you start at the mean of 180, you have to move positive 2.33 standard deviations in order to get to the data point that you want. So if you start at 180 and you move 2.33 standard deviations, each standard deviation is 20 pounds. So that means you're adding 2.33 times 20. So this is another way that you can get the same answer to represent your data point. So either plug it in mechanically, the z-score formula, or use the definition for what it means to be a z-score. Any questions? All right, so that's where we left off last time. So what we've done so far is we found the probability that this variable is greater than a certain number. We said that was the same as an area to the left of the bell curve, or greater than is an area to the right. Variable less than the number is an area to the left. And in both cases, we've reduced finding probability by finding area instead. So let's say I had asked you, what's the probability of a weight being exactly 215 pounds? This is a little bit tricky. So based on what we talked about, we've reduced the idea of finding probability to finding area instead. So at 215, we can think about this as, so before, if we want to find the probability of a man weighing between 215 and 230, for example, that would be the same thing as finding the area in between, under the bell curve. But now if we want to find the probability that he weighs exactly 215, basically this region here between 215 and 230, imagine these as walls and they collapse into each other. And once they collapse into each other, you want to find the area in between those walls at exactly 215. So what would that area be? That would be consistent with finding the probability that the weight is exactly 215. So imagine this region collapses and then you find the area in between.
So is it gonna be 214 and 216, or is it 214 point whatever?
Okay, very good. So based on what we've talked about so far, if we had done just 215, where these two regions collapse into the data point 215, then mathematically what would that area be?
Be 222.5.
What is it?
Will be near 222.5.
Well, how are you getting that?
I just did the average between.
Oh, no. So we're saying that if the question had been, what's the probability that a man's weight is between 215 and 230, then conceptually we're just finding the area under the bell curve between these two regions, so this black region, right? And then if I ask you what's the probability that a man weighs between 215 and 220, then instead of 230, this wall moves to the left, and now you're only finding the area between 215 and 220, if that was the question. But now if I ask you what's the probability of being exactly 215, then both these walls basically collapse into 215, and you're finding the area in between those two walls on the bell curve, so what would that area be? I don't think I'm asking that question. Okay.
You answered it right.
So let me try again. Okay. So if I had asked, what's the probability, forget this for a second, what's the probability that a man's weight is somewhere between 215 pounds and 230 pounds? So that was one of the questions we did last time. And we equated this idea of a probability to the idea of an area. So this will be the same as the area between 215 and 230 under the bell curve. So it's this black area here. So the way that we find that area, we said to find the z-score of each one, so that we can find the left area of each one under the bell curve. So let's practice that. So what would this, how do you find this area?
You take the area under 230 and subtract the area under 215.
Okay, good. So based on what we talked about, we know how to find the left area relative to any z-score using the z-score chart. So we're going to find the left area of 230, and we're going to take away the area of 215. And then that's going to leave us with the area that we want in between. So the left area of 230, as practice, let's calculate that. So the way that we do that is we need to calculate the z-score of 230. So that'll be 230 minus 180 over 20, and that'll give us 50 over 20, 2.5 things. So go ahead and look up 2.5 as a z-score, and let me know what you guys look there.
0.9938.
Yeah, so the left area of 230 is 0.9938. So then we're going to do the same thing, calculate the area of the left of 215, which we did before, 0.9599. And if you subtract these two, the total, this answer will end up being So this means that the probability of a weight being between 215 and 230 is only 3% of the time. And so we get this probability by calculating the area between this region under the bell curve. So what if the question had been, what's the probability of a weight that's between 215 and 218? So then this, instead of this 230 being this right wall over here, the wall moves until you hit 218. And now to find the probability of a weight being between 215 and 218, instead, now you have this smaller area instead, and that represents the probability. Okay, so that would be the probability of a weight between 215 and 218, instead of 215 and 230, right? But what if I had asked you, what's the probability that a weight is equal to 215? Well, that would mean instead of this region that's defined by these two walls, both walls are exactly at 215. So in calculating this probability, we're measuring the space inside between those two walls under the bell curve. But if our data point is exactly 215 and both walls are on that data point, then what is the area of the space inside those walls?
0.
0, good. So mathematically, the probability of this variable being exactly equal to this number is actually defined to be 0. And this should feel kind of weird, it should feel counterintuitive, because if you think back in real life, this is implying that the probability that somebody in real life, a man in real life, weighs exactly 215 pounds is 0 or impossible, and that doesn't seem to make sense. So we can reconcile why mathematically this probability of being exactly equal to 215 pounds is 0, yet in real life you're bound to meet somebody who weighs 215 pounds.
Because you're not looking at one person specifically, you're looking at a distribution of people.
Okay, we're on the right track. Anybody want to add to that?
So in this equation, the chance of you finding a person who's exactly 15 pounds seems to be 0 because you're looking at a population of, in this case, it's weights of men, so 3.5 billion people, if that's roughly half the population of the earth. So it's just an extremely small, I guess, chance.
Okay. So on the right track. It's getting warmer. Anybody want to add to that?
I had, but I lost it.
Okay.
So do you have like lurking variables going on with that too?
Okay. So let's build up for this. So on your homework, you had a little bit of practice on some vocabulary terms on what it means to be a continuous variable versus a discrete variable. And we didn't talk about it before because there was not a context to talk about it in. But in this case, there's an important context for that distinction. So when we talk about a continuous variable versus discrete, let's start with discrete.
Has a finite amount of numbers and measurements and sets.
Oh,
So
excellent.
at the end of it, it's going to be, you had this many trials with this many people, and this is your number exactly. Where continuous can be measured or quantified continuously or infinitely without breaks for the measurement standard you're using.
Okay, very good. So let me basically say the same thing, but phrase it maybe differently. So for a discrete variable, let's start with an example. Let's say that your variable is points in a basketball game. There's points in any game, whether it's basketball or football or hockey or volleyball or whatever. So this represents a distribution, which means on the x-axis, you want to list out all possible values of your variable. So we'll do, you can't have negative values in the game. So 0, 1, 2, 3, and so forth. And then for each one, we indicate the probability or how often it occurs in the game. And then you might see a distribution that looks like this. So then at the end, you have a distribution that's basically a bar graph with a whole bunch of gaps in between. So why do you think there are all these gaps in here?
Because for like half points and stuff like that.
Yeah, the gaps represent values that are just not possible for this variable. You can't have 2.6 points in a basketball game, right? You can only have this whole number of points, and the heights of the bars represent how often each value is possible. And the gaps represent impossibility for those values. So this is a discrete distribution, meaning that there are only a finite number of values that have representation. All these points with the gaps, it's not possible there, so there's no representation. If you compare that to continuous distribution, what we're talking about now is a continuous distribution. Bell curves are continuous distributions. So what that means, if we're talking about weight, for example, that means we're implying that all values in this continuum are all possible. If you have somebody So theoretically, it's possible to have somebody who weighs 180.1246 pounds. That's considered a different weight than somebody who weighs 180.1247 pounds. Right, so, and just by looking at the picture, you can tell that it's continuous because you can draw this distribution without lifting your pen. Versus over here, to draw the distribution, you have to draw each bar one at a time and then stop and go. So, going back to this question of what's the probability that somebody weighs exactly 215 pounds, well, because this is a continuous distribution, when you say 215, you're implying it's exactly 215, basically 215 followed by an infinite number of zeros. So that exact number, that probability is defined to be 0. And in real life, when we ask what's the probability that somebody weighs exactly 215, we don't really mean exactly 215. We mean somewhere between a very concentrated region. So in real life, when we say that somebody weighs 215, we're probably, based on how we round numbers, meaning 214.5 to 215.5. So now you have a region, and that region has an area associated with it under the bell curve, and that'll be a non-zero area or non-zero probability.
That's why I asked the way I did, is like, are we talking about?
Yeah, exactly, that was
214
definitely.
point, or is it 214 and 216? Because I didn't know what you meant by the area because the parameter was left open.
Exactly, so mathematically, if we ask what's the probability that this weight is 215, mathematically that area is 0, that probability is 0. But then, if in real life, practically speaking, we need to assign for a continuous variable to find any probability, since the probability of that point is 0, we need to assign a region around it in order to find that area and hence the probability. So a takeaway from this is to find probability for a discrete distribution, you look at a single point and you just find the height of that bar, and the probability of that point, for example 2, is just whatever the height of that bar is. But in a continuous distribution, for a probability of a certain data point, it's defined to be 0 because to find the probability in a continuous distribution, you're looking for area. And the area of a single point is 0. And along those lines, if I were to ask you, for this discrete distribution, what's the probability that this variable, points in game, is at most 2? Well, at most 2, logically speaking, means what? At most 2 means the highest value possible is 2, and it could be anything lower as well, so 2, 1, 0. So, in this case, the probability that the point is at most 2 is either 0 or 1 or 2. And then to find this probability, because you have probability of events drawn by OR, this is the addition rule, so then you would find the probability of each one added together. So then you would find the probability of getting 0 points, let's say 0, 2. So then the height of whatever this bar is, plus probability of 1, which is the height of this bar, plus the probability of 2, which is the height of this bar. So to find probability of a discrete distribution, taking on certain values, you would add up the individual probabilities with the individual heights of the bars. That's the probability of a discrete distribution. So if you want the probability of values in a continuous distribution, remember we said that in a continuous distribution, probability is area. So if you want the probability of being less than 180, for example, then unlike the discrete distribution where you're adding up individual discrete values, here you're finding continuous areas. So here, the weight being less than 180 means that you're finding the area of this region. That's the left way. So to find probability in a discrete distribution, add up the heights of the bars. To find the probability in a continuous distribution, find relevant areas. Okay. Any questions?
Are there gonna be defining terms later on, looking at examples like this where it's greater than or equal to, or is it just gonna be the greater than or less than?
Okay, great point. So that leads us to the next thing. So we just said that the probability, mathematically, the probability that a weight is equal to 215 is 0. And before we answered the question of the probability of a weight being less than 215 was 0.9599. So what if I had asked you what's the probability that a weight is less than or equal to 215? Where I just include that equal as a possibility. So how do you think this answer would change?
I think it will be displayed differently. I don't think your answer would change at all.
Okay, what do you mean displayed differently?
So if you were doing that on a graph, right, so whether it's a dashed line or a solid line indicating what is that, right? So if it was the solid line, it's this and everything following. If it's the dashed line, it's everything except that.
Oh, okay, good. So to extend that, if you were just being asked what's the probability that the weight is less than or equal to 215, so the number, should it be the same or different?
I believe it should be the same.
Okay, you guys agree? Okay, good, very good. So it should be exactly the same. And the reason for that is the only difference here is you're allowing this weight variable to include this one data point of 215 in addition to everything else that came before it, less than 215. Now the only difference is you're including this data point of 215, but we said the probability that this variable includes that data point of being exactly 215, that probability is 0. So basically you're just adding 0 to the previous probability, and adding 0 is just itself. Okay, that's why it's exactly the same. So in a continuous distribution, whether you include that boundary point or not, it doesn't matter. Any questions? But in a discrete distribution, does it matter if you include the boundary point? Like if I say the probability of getting less than 2 points versus the probability of less than or equal to 2 points, does that make a difference?
Yes.
Yes, good. Because to find probabilities in a discrete distribution, you're adding up the heights of these bars. So
For the first one, you're doing ones that are less than 2. For the second one, you're including 2 in that sum.
exactly. So the first one, less than 2, means you're only including the height of the bar for 0, the height of the bar for 1. But in the second case, you have to include the height of the bar for 2 as well. So there's another value that's included there. Okay, very good. Any questions? So that's why the distinction between a continuous distribution and a discrete distribution is important, because the way that you calculate probabilities for each one differs. In the case of a continuous distribution, it's using area. In the case of a discrete, you're adding individual heights of bars. Okay. So now you guys should be comfortable if anytime a variable is told to be in a normal distribution, a bell curve, you should be comfortable finding any probabilities of values in that bell curve. So for example, the probability that a weight is greater than 215, that a weight is less than 215, that a weight is equal to 215, that a weight is between 215 and 230, you should be comfortable finding that probability. And it turns out that using the tools and framework we talked about, that probably is easy to find because of the existence of the z-score table, where there's this relationship that's given for you for finding the left area given the z-score. So this framework makes it easy to find those areas or probabilities. So another question is, what if you have a situation where the variable is not distributed in a bell curve? And that happens a lot in real life, where if your variable, instead of a bell curve, could look like this. Let me try. So just to put context into this, if you were to go out and collect a whole bunch of cholesterol levels in patients. So let's say that you look at individual cholesterol. And cholesterol is measured differently. There's at least 2 different ways to measure cholesterol, HDL, or good cholesterol or bad cholesterol. But let's say that we agree on a certain convention, and the cholesterol that's measured ends up looking like this. And so this is a reasonable distribution for cholesterol, and definitely doesn't look like a bell curve. So who can give some rationale as to why this might be reasonable for cholesterol?
Variance in the time the sample was taken in between meals.
Okay, so basically what this is saying is that there's some cholesterol level that's very low, that a lot of people have that low cholesterol level. And vice versa, there's some cholesterol out here that's higher, and a lot of people also have that high cholesterol level. So what could explain that it's typical for people so one group of the population to have low cholesterol and one group of the population to have higher?
Types of diet.
Yeah, good. So cholesterol is something that can be regulated, that can be controlled based on lifestyle choices and so on.
Yeah, I mean, I think it's several, it's like, so ones that exercise or don't, depending on your control study, amount of sleep and rest, types of diet, and then types of anxiety or stress they're actually under and producing. So it
Very
depends
good.
on which way you're trying to look at that study.
Very good. So all those things point to how cholesterol could be influenced and how it can be controlled. So people choose to live healthy lifestyles or don't, and that affects which part of the population they belong in, whether they have low cholesterol or high cholesterol. And a lot of people end up having one or the other. That explains the shape of that distribution. So the point is, there's a lot of variables in real life that are not distributed as a bell curve. This is an example of that. So the question is, what if we wanted to answer the same question of what % of the population has cholesterol levels between these 2 certain ranges? And so let's say, I'm gonna make up numbers here. Let's say the mean is 190. And let's say we wanted to find what % of the population has a cholesterol level between 210 and 230. So because this is not a bell curve, we cannot use those tools that we had talked about to find the z-score, look it up in the z-score chart, because that only applies to bell curves. So it would be awfully wasteful if we're not able to apply that same bell curve framework to other problems, because we have such a clean framework. So in the rest of chapter 6, what we'll talk about are the instances in which we can apply that bell curve framework to other problems which might not necessarily be inherently bell curves in themselves. So we're going to talk about situations bell curves are used, at least in this class. So the first situation is the easiest situation, which we talked about already, is that it's given to you or observed by you that the variable is distributed as a bell curve. So given or observed that variable is distributed as a bell curve, and I'm just gonna say that it's normally distributed, so same thing. So for example, i.e., if you're told that weights of men are normally distributed, and then you're asked to find the probability that a weight is less than 215 pounds, then you're told that that weight variable is normally distributed, and then you can use the bell curve tools that we talked about. So this is the simplest, most straightforward case of using bell curves, is that you already know that the variable in question is distributed as a bell curve. So we've already talked about that case. So now let's talk about the next case, and chapter 6 has 2 remaining cases, and I want to give you guys a heads up. These 2 remaining cases constitute the most confusing concepts of the entire semester. And I tell you that not to scare you, but just to, just so that you can pay extra attention and ask questions, because objectively that's true, that these remaining 2 concepts are the most confusing of the whole semester. So this second concept here is what we call the central limit theorem.
So that's in section 6.4.
Yeah, this should be 6.4. So, I'm going to build up to the central limit theorem. So let's start with one of those variables we said was not distributed in the bell curve, like individual cholesterol. So let's say that you go out to the general population, the whole country, and you randomly select people and you test their cholesterol levels. And then you build a histogram of the number of people who have each level of cholesterol. And let's say that the distribution looks like this. It has 2 different peaks. One peak at a lower cholesterol and one peak at a higher cholesterol. So this variable is individual cholesterol level. So that means the cholesterol level of each person, and then you count the number of people who have that individual cholesterol. And that gives you the height at each point. So for each individual cholesterol level, you look at the probability for how often each individual cholesterol level occurs. So we already said that this variable is not distributed in a bell curve. So let's say that you were to, instead of sampling the whole population, the whole country, you gather a random sample, let's say 100 people. And then you test each of the 100 people's cholesterol level. And then you plot the histogram, how often each cholesterol level occurs. So what do you think the shape of that histogram would end up looking like? The shape of that distribution.
Would it be similar to the distribution for the population?
Okay, very good. So for the population, it was for all 300 million people. This is only for 100, but the general shape should be similar, even though you have fewer data points. It'll still be similar to this. And let's say that in the general population, the mean cholesterol level was 190. And let's say the standard deviation is 10. So, if you look at individual cholesterol here, the mean of the standard deviation will be similar. Will be 190 and 10 for the standard deviation. So let's say that you continue, and you gather another sample of 100, and you plot the distribution of that. What do you think the distribution looks like? So similar? And so forth. Let's say you repeatedly gathered different samples of size 100. The histogram should look, or the distribution should look exactly the same, or similar. And let's say that you repeated this process a number of times that approaches infinity, like 1 billion times. So 1 billion times you gather different samples of size 100. Okay, so let's say that for each sample size 100, so that you have 100 individual cholesterol numbers for each of 100 people, you reduce all those 100 cholesterol numbers into a single number by means of the average. So you take the average of each sample of size 100, and so the sample mean is given by the symbol x bar. So for each sample of size 100, you find the sample mean. So at the end of this, how many sample means do you have?
1 billion.
Yeah, 1 billion, good. So 1 billion samples of size 100, each sample has its own sample mean, so at the end you have 1 billion sample means. So let's say for those 1 billion sample means, now you plot a distribution of each sample mean, and for each value of each sample mean, you plot how often each one occurs in the group of 1 billion. So what do you think the shape of that distribution should look like?
That will look like a bell curve.
Okay.
because
So the suggestion is that this should look like a bell curve. You guys agree? So why do you think it should look like a bell curve and not the original?
So you take in your samples from the standard point, you averaged all those samples, and then you did it a whole bunch of times, right? So now you have data points that are saying, this is all the ones, here's my highest part, here's the ones all going down, that defines a bell curve, right? So I'm going from the lowest to the highest, raising up big and falling down, so there's no individual changes in that.
Okay, very good. Excellent. So let me add to that. So every sample size 100 here has the full range of individual cholesterol levels as the original population distribution. Has the full range, but once you take the sample average of each, now there's this huge smoothing effect where this sample average becomes some number that's clustered very tightly around the original mean of 190. So the first time you take the sample average, it might be 188. But that sample average is not going to be the smallest possible value because it's smoothing out. So it's going to be somewhere in the middle here. So it'll be, let's say, around 188, or close to the original mean. And if you take another sample and you take the sample mean there, you'll get another number that's close to this number and 190. You might get 191 in this case, and so forth. So all these sample means will be grouped really closely together. And they won't have this huge variation that the original variable representing individual cholesterol did. So this sample mean represents average or mean cholesterol out of 100 people. So, or, let me use more general terminology. So in a sample of 100, so in the end, all these sample means that have values really close to the original mean of 190 end up having this bell curve shape where the most commonly occurring value is that original mean of 190. And then you could possibly have values around that, but the farther you are from 190, the lesser the chance of that. So in the end, you have the both. Any questions so far? Okay, so this is a very important idea in statistics that we call the central limit theorem. So the central limit theorem says that no matter what the individual distribution of individual values looks like, the resulting distribution of sample means will be a bell curve. And not only do we know that this resulting distribution of sample means is a bell curve, but we know the mean and standard deviation for this bell curve. So it turns out that the mean of this bell curve will end up equaling the original population mean, in this case 190, and the standard deviation of the bell curve. So let's talk about standard deviation. Standard deviation measures how spread out the numbers are from each other. So if the original distribution has a certain spread, the new distribution should be more spread or less spread. Should it have less variation or more variation?
Less.
Yeah, why do you think it's less?
Say it's less because the original graph here is not a bell curve, not a bell graph at all. It comes up with 2 points, whereas the bell graph that we now have with all the sample means only has 1 point, which is the mean there. So there's more values surrounding that original 1 point than there is for these two.
Okay, excellent. So when we ended up taking the sample means for each sample, we had this huge smoothing effect where the numbers all clustered tightly around 190. And the tighter you cluster, the less spread there is, and the standard deviation will be lower. So in the end here, this resulting distribution will have a lower spread or a lower standard deviation than the previous one. And we reflect that with this new standard deviation will not equal the previous standard deviation, but it will be that divided by the square root of n. So when you divide by a number that's greater than 1, then you end up reducing the quantity. So here we end up with the original standard deviation, but divided by a number. So this result will end up being a smaller standard deviation than before. So the point is, the central limit theorem says that no matter what the original distribution of individual values looks like in terms of its shape, that the resulting distribution of sample means will end up being a bell curve with this mean, which is the original mean, and this standard deviation. And that standard deviation is not equal to the original standard deviation, but a function of that standard deviation. Specifically, standard deviation divided by the square root. Okay. So right now this is all very abstract. We'll use a concrete example so that this will be much clearer. But for now, we have to talk about what this means first. So it turns out that there are important assumptions that have to be true for the central limit theorem to be true. And so let me summarize what the central limit theorem actually is in words. So the central limit theorem says that the distribution of sample means is normally distributed with a mean equal to the original population, equal to the population mean of individual values. And the standard deviation is equal to population standard deviation divided by the square root of the sample size.
It's still gonna be sigma divided by the square root of the number.
Yep, so the sample size is the n that we talked about. So, just in this case, when we have this resulting distribution of sample means, we said that this has to be a bell curve, and also, so let's find the mean and the standard deviation together. So what should the mean be?
Clustered around minus 190.
Clustered around the original population mean of 190. So in this example, this mean will be 190. And then the standard deviation will be the original standard deviation, which is 10, but divided by the square root of n. And n is the sample size, each of the individual samples. So the sample size in this case is 100. So then it would be 10 divided by the square root of 100, which is 10 divided by 10, which is 1. So just like we said, the original standard deviation or measure of variation, the measure of spread, is 10 originally, then the new one in the new bell curve, it has to be less spread. And indeed, the number 1 is less than 10. Any questions?
So that's the average of sample. I thought it was gonna be, sigma over the square root of 1,000,000,000 times, and I'm like, man, that's gonna suck.
Yeah. So n is the size of each of the samples.
Individual samples.
Individual samples, yep.
Not the number of times. That turns into a different part, okay.
Yeah, the number of times just says that we assume that the number of times approaches infinity, because if that's true, then the closer the answers in practice end up equaling this.
No, so it's making sense to me, I'm just compressing where the data needs to go, right? So
Yeah.
you did it 1,000,000,000 times, so you could actually take the weird thing and put it into something that looks like an empirical rule for a bell curve, right? So now, based on the averages for your individual sample size, the number that was used in it is gonna be the square root of your original standard deviation that you can use with your mean to use the z-tables.
Yes,
That's how I'm putting my data together, unless I said something wrong.
That's right. Any other questions or comments? So the point is that the original distribution of individual cholesterol levels is not a bell curve, but if you're to be asked the probability of a sample mean being between two values, then now you can use that bell curve framework that we talked about. And you can use the z-score and look it up in the chart. So we'll do that in a bit, but now we know the correct mean and the standard deviation for this resulting bell curve. So it turns out that there's an important assumption that needs to be true. So the gist of this is that you can have any funky distribution to begin with, and because for each sample, you're taking the sample mean of each sample, and you're smoothing out all these numbers by way of the mean, then because of that, you end up with a distribution that is a bell curve. But let's say that for each sample, instead of a size of 100, let's say that you only have a size of 1 for our sample. Then in that case, if we take the sample mean, then that sample mean will be that original value. And if we take the distribution of all the original values, do we end up with a bell curve? No. So what shape should we end up with if each sample size was 1? And then we took the average of that 1.
Population.
It should be the same as the population.
Yeah, it'll be the same as the original population distribution of individual values. So the point is that the size of the sample matters. Is if it's too small, then you don't have the smoothing effect when you end up taking the average of each sample. So an assumption is that the size of the sample, or the sample size, needs to be large enough but large enough is hand wavy, and it turns out that through years of empirical evidence and also mathematical proof, people have determined that large enough means that it should be at least the size of 30. And 30 is actually not that bad. It's not even that large. So you have a sample size that's at least 30 people here. Then if you were to take the average of each of the samples of size 30, then that creates enough of a smoothing effect so that when you go to plot the distribution of the sample means, you'll end up with a bell curve. Any questions? So let's say that this assumption had not been met, and the sample size were not at least 30. So let's go back to the previous case, where let's say that the sample size isn't big enough and it's only of size 1. Central limit theorem is basically saying that we want our original distribution to end up looking like a bell curve. But what if the sample size isn't at least 30, what if it's only 1? Then what does the original distribution have to look like for the final distribution of sample means to look like a bell curve?
It has to originally be a bell curve.
Or it has to originally be a bell curve, very good. So in the assumptions, either the sample size has to be large enough, or only one of them has to be true, or the original distribution has to already be a bell curve. Original distribution of individual values already bell curve.
Why would you multiply or take samples of only one at a time going back in to verify something?
Okay, so the one used in the example was only an absurd example, but if not one, it might be 10, or it might be 20. But the point is that those are still smaller than the required minimum sample of 30.
So you use the central limit theorem.
Right.
Okay, right.
Alright, so this is what the central limit theorem says, and this is the assumption, and only one of them has to be true, either one or the other. So let's go ahead and look at a concrete example. Let's go back to our example where we're talking about weights of men. And we're already told that weights of men are normally distributed. And let's say we're told that the mean is 180, and the standard deviation is 20. So the first question is, let's say that you randomly select a single man. And you want to know what's the probability that his individual weight is more than 200 pounds. So then in this case, you're being asked for this variable, individual weight, and the probability that that continuous variable is more than this number. So remember, we said that to find a probability for a continuous variable, that's the same as area. So in this case, we're looking for the area that's to the right of 200 under the bell curve. So 200 is here, and we want the area to the right. So this gives us the area to the right under the bell curve for this weight variable, which is also the same as the probability that this weight variable is greater than 200 pounds. So this is actually the first situation that we talked about in our review today, the most simple, which is we're told that this weight variable is distributed as a bell curve, and we want to find the probability that the same weight variable is greater than the number. So it's the same as the area to the right of this number under the bell curve.
The z-score only figures out the left, so understanding that your one standard deviation greater than 180 divided by 20, so 1/20 put to a decimal, subtract that from 1, get your z-score and apply.
Very good. So let's step through it. So exact same steps. We're going to take this data point of 200, find the z-score relative to a mean of 180. And so that'll be the data point minus the mean, which is 20, and then divide by 20 pounds for each one standard deviation. So that'll give us a z-score of exactly 1. So then we look up that z-score of 1 in the bell curve table, in the z-score table, to give us a left area.
0.8413.
So left area is 0.8413. But we want a right area, since we want the probability of being greater than that number.
So subtract that from 1.
Subtract from 1. Okay, so it looks like 1.1587. Okay, so this tells us that the probability that a single man would weigh more than 200 pounds is 15% of the time. So let's say that we had the next question. So now let's say that you select a sample of 100 men, and you want to know what's the probability. So let's say that in that sample of 100 men, you weigh all 100 men, and then you find the average of the 100 men's weights. So mean weight found. So you want to know the probability that that mean weight in the sample of 100 is more than 200 pounds. So these two questions look very similar to each other. This is one and the one that we just did. But conceptually, they're actually very different. In the first question, we're asking what's the probability that one single man has an individual weight that is more than 200 pounds. In the second case, we're asking what's the probability that the average weight of 100 men that we're observing is more than 200 pounds. So there's a conceptual difference, but the question is there a quantitative difference? So do you think that this answer should be the same as before, or if not, less than or greater than? Okay, vote for the same, or the rest of this?
There's too many lurking variables.
I think it should be greater than?
Okay, vote for greater than, anybody for less than?
I'm gonna say it's entirely dependent on where that sample is being taken from, because you don't know where you're at or who you're getting it from, right?
Okay, good, so that's a good point, so we're assuming that it's a random sample. And granted, that's a strict assumption as it is, but let's assume it's perfectly random.
It should be somewhere close then.
Okay, so a vote for somewhere close or equal. Anyone else? Anybody who has abstained from voting?
Plead the fifth.
We're not in court.
Okay. Alright, so let's talk about this. So instead of a sample of 100, let's look at a simpler example where you only have 10. And instead of a sample of 10 people, you have 10 numbers. Let's say that I want the average or the mean of those 10 numbers to be greater than 100. In the previous example, we wanted the mean of 100 numbers to be greater than 200, but let's say in this example, we want the mean of 10 numbers to be greater than 100. So if you look at each of the 10 numbers individually, as a whole, what must be true if the average of them must be greater than 100? Or let's just say, for simplicity, equals 100. So we want the mean of 10 numbers to be equal to 100. So what must be true about each of the 10 numbers as a whole?
If they are at least 100.
Yeah, so if you want the average of them to be 100, then as a whole, they're going to be equal to 100. And for every number that's not equal to 100, you're going to have another number that must offset it by that much, and so that the average is 100. So if the average is 100, one number is going to be 100, another number might be 90, but if this number is 90, there must be another number that offsets it by the same number, amount.
10.
So another number must be 110. And so forth. If one number is 99, another number must be 101. So that the average of all these numbers is 100. So same thing here, if the average weight of 100 men is more than 200 pounds, then that means as a whole, each of the 100 men must be 200 pounds. Must be greater than 200 pounds. And for everyone who isn't at least 200 pounds, there's somebody else who offsets it and is heavier by an equal amount. So we say that as a whole, each of the 100 men are required to weigh more than 200 pounds. So in the previous situation, you're only requiring one man to weigh more than 200 pounds, and the likelihood of that is 15%. But in this case, essentially you're requiring all 100 men to weigh more than 200 pounds, so do you think the likelihood should be more or less?
Less.
Likelihood should be less, very good. So this probability will end up being much less than this probability. Any questions? Okay.
Are they gonna word it the same way you just did, or is it gonna have something that defines what we're trying to give an analysis on?
So don't look for specific wording, but the conceptual idea that's conveyed by the wording should be the same. So in other words, in the end, they're looking for an average value of a group of people. So here the group was 100, so we're looking for the average value or weight here of the average of the group of 100. So maybe a word that'll be a sample mean or the mean weight of a sample, anything that captures the average value of the group.
And I do understand that part. The reason why I was asking it in that particular order is because we have our normal average over here for your distribution of weight for men in the population, counting like everybody, it's an assumption. Because the normal is, your mean is 180, and then your standard deviation is 20.
Okay.
But we're trying to do a different sample with this estimate and calculate the odds. So we're still gonna end up using the original to figure out that part. I'm just, sometimes you don't see the tables at the same time, that's
Okay,
why I was
okay,
trying
good.
to.
So right now, we recognize that, first of all, these two questions are conceptually different. One is dealing with the probability of individual weight being relative to this number. One is dealing with the probability of a mean weight of a sample being relative to this number. And so now that we recognize there's a difference, let's try to approach it the same way as before. We're gonna draw a picture. So before, what we did was this variable that was involved in the probability, we drew the distribution for that variable. So the individual weights of men, we were told that individual weights are distributed in a bell curve with this mean and the standard deviation, so we drew that specifically to what was described and given to us. The weights of men are distributed in a bell curve with this mean and the standard deviation. And that was the variable involved in that probability. So now we look at this new probability, and we look at, this is the variable involved, which is the mean weight in a sample of 100. So we're gonna draw a distribution where the x variable is mean weight in a sample of 100. So before, our rationale for making the shape of this distribution a bell curve was that we were told that weights of men are normally distributed. That was just flat out given to us. So in this case, what's the rationale for us drawing a bell curve here? It's never told to us that mean weights in a sample 100 are normally distributed. It's only told that individual weights of men are normally distributed. But how do we know to fit a bell curve here? So this comes directly from the central limit theorem. So the central limit theorem tells us that the distribution of sample means is normally distributed. And that's exactly what our variable represents here. It's a sample mean, or it's a mean value in a sample of a certain size. So because we have a variable that represents a sample mean, we know that that's going to be a bell curve. Now, as long as the assumption is met, so let's verify that now, either the sample size needs to be large enough, at least 30, which is it here? Yeah, it is. So then we're done. We don't have to check the other assumption because one of them can be true, not both. Both don't have to be true. Okay, so now that we verified that the central limit theorem holds, that the distribution of sample means is indeed a bell curve, normally distributed, now we can get exactly the mean and standard deviation. Yeah.
Is that for everything, or that's just for this problem?
Yeah, this is for any distribution.
It has
As
to be
long
more
as
than
the
30?
sample size is at least 30, then the distribution of the sample means will always be a bell curve. So now that we established the central limit theorem holds and we have a bell curve for this distribution of sample means, now we can get the exact mean and standard deviation using the central limit theorem. So the mean will be the original population standard deviation, or the original population mean, which in this case is 180. So the mean of this new bell curve is 180. And the standard deviation of the new bell curve is the original population standard deviation, but divided by the square root of the sample size. So that's going to be 10. So standard deviation will be 20 divided by the square root of 100. So 20 divided by 10 will be 2. So now that we got the correct parameters for this new bell curve, now we can proceed exactly the same as the previous case for bell curves. So find the z-score, look it up in the chart. So let's find the z-score of this data point of 200. So the z-score will be 200 minus the mean, 180, divided by the standard deviation of 2.
And that's 10.
That's 10. Good. So again, we're looking for the probability that this variable is more than 200, and that will be the same as finding the area to the right of 200 under the bell curve. But our z-score here is 10. So that means it's 10 standard deviations away from the mean. That means it's very far right on this bell curve. So we're basically finding an area of a data point that's very far right to the bell curve. That means the area to the right will be very small because it's so far right. So again, it's, let me continue it out here. So it's so far right, that it's all the way over here. So this is a z-score of 10. So we're looking for the right area, which will have this tiny area here. So if you try to look that up in the chart, if I try to find the z-score so that you can get a right area, what happens?
The book says for z-scores above 3.49, use 0.9999 for the area.
Okay, good. So let's talk about that. So let's, for a particular z-score, let's look at the left area and then let's look at the right area. So the z-score in the book tops out, maxes out at 3.5. So if the z-score had been 3.5, let's say here, what would have been the left area?
0.9999.
Yeah. And then what would have been the right area?
0.0001.
Okay, good. 0.0001. But that's for a z-score that is 3.5. But our z-score is way more than that. It's 10. So our z-score being 10, what would be the left area relative to 99.99%? Less than or greater than? For left area.
Greater than?
Yeah, it would be greater than because the left area for z-score 3.5 was here. That's the left area. And our z-score is to the right, so the left area will be more. So the left area here is greater than 0.9999. But we're ultimately looking for the right area. So our right area will be greater than or less than 0.0001.
Be less than
Less than.
0.0001.
Yeah, less than 0.0001. So that's the best conclusion we can make from the chart. It turns out to be a lot less than 0.0001. But to get that exact number, we can't use a chart that has only granular values. We can only use a calculator or a computer to calculate this exact number for us. But for now, this is good enough. We just know that it's some tiny number. It's going to be much smaller than 0.0001. So the point is that if you have a sample of 100 men, the probability that the average weight of this group of 100 men is more than 200 pounds is going to be less than 0.01%. It's very small. Compared to if you have one man, the probability that he'll weigh more than 200 pounds is 15%. So that's much more. Any questions? Okay, so the point is, if you have a probability where the variable involved represents a sample mean or a mean value in a sample, then we can use the central limit theorem as long as the assumptions are met and we can use a distribution that is a bell curve. So one last quick thing that's related. Let's say that instead of selecting 100 men, where we were able to use the central limit theorem, let's say we had only select 10 men, and we asked the same question: what's the probability that the mean weight in a sample of 10 is more than 200 pounds? can we do the same steps that we used before and use a central limit theorem?
Yes, you can,
Yeah, wasn't it?
because your second part is met, the original distribution of individual, values already is in the bell curve.
Yeah, very good. So as long as the assumptions are met, but the assumption is either one of these two can be met. So in this case, the sample size isn't at least 30, but the second assumption is true, which is the original distribution of individual values or weights of men is already a bell curve. And because of that, you can still use the central limit theorem and use the exact same steps. Where the mean is the original population mean, the standard deviation is that divided by the square root of that. But the square root of n here will be the square root of 10. And then everything else is the same. Find the z-score. Oh, one last related thing, and then we'll be done. So here I asked you, what's the probability of the average weight of 100 men is more than 200 pounds? But let's say I had asked you, what's the probability that the total weight, if you add up the weights of all 100 men, but it's going to be more than 20,000 pounds. So the central limit theorem only deals with the distribution of sample means as your variable. But your variable here is a total value in the sample. So how do you think you can, so how do we know what the distribution looks like where the variable is a total value and not a sample mean?
So take your total weight and divide it by the sample mean, and you should have your average.
Okay, very good. So basically we can convert this total weight, total value in a sample to a sample mean by dividing by the size of the sample. So if we divide, so this variable representing total weight can be converted into an average weight of the sample, so a mean, by simply taking the specified total and dividing by the sample size. So if you divide that, then you've converted a total value in the sample into a mean of that sample. And so now you have this situation, and now you're back to where we started before. And now we can just use the central limit.
One too many zeros.
Oh, 20 items. Any questions? Okay, so if it's not completely clear now, the homework should help a lot with that, and then we can keep talking about it next time.
As long as you can get this part to where, this is just understanding that you've gotta convert your signal, and I've got the answers to do that now, so.
Okay.
I got about halfway through the homework last night, and number one, I ran out of time, number two, I ran out of grades, and
Thanks, okay.
be good or be good at it, I'll say it like that.
Yeah, you too.
So, our next test is next week, or at the end of next week, right?
Yes.
Okay, so I wanted to ask, I don't know if it's like